So I want you to just imagine for a second that you're sitting behind the wheel of a brand new, totally state-of-the-art electric vehicle.
Right, you've got that new car smell.
Exactly. And you're cruising down the highway, maybe doing 70 miles an hour. The music is playing. The cabin is just dead quiet.
It's that, that effortless silent glide that EVs are so famous for.
Yeah, everything feels perfectly smooth. And then completely out of nowhere, you just lose power. Like the car just goes entirely limp.
I mean, it is a genuinely terrifying scenario. You press the accelerator, and there is just nothing there.
Nothing at all.
Right. The vehicle is coasting, and you have to somehow, navigate across 3 lanes of highway traffic to the shoulder without any propulsion.
And here is the truly crazy part about this specific scenario. Like when you actually get the car to the mechanic, they tell you it wasn't the massive high-voltage battery.
Right. It's not the obvious thing.
Exactly. It didn't fail because you hit a pothole or, got into a fender bender. That entire catastrophic loss of power happened because of a microscopic spark.
A spark that acts like a tiny bolt of lightning.
Yeah, and a physical wiggle inside the motor that is, smaller than a single grain of sand.
And it really sounds like science fiction. Or, at the very least, it sounds like an impossibly fragile design,
It does, because we are so used to thinking about vehicle failures in, macro terms.
Right, a blown tire, a snapped fan belt, a cracked axle. You can physically see those things.
You can hold a broken belt in your hands.
Exactly. But in modern dual-motor electric drive systems, the most devastating failures, they don't start with a bang. They start at the molecular level.
And today, we're going to figure out exactly how that happens. I'm your host, by the way, and I'm here with our resident engineering expert for this deep dive.
Glad to be here.
So we've gotten our hands on a highly detailed, honestly, incredibly dense engineering roadmap today.
It's a heavy one, yeah.
Yeah. The source document is entirely focused on motor body failure mechanisms and diagnostic prevention standards.
Specifically, it breaks down mechanical wear and vibration failures in these really high-performance double-motor drive systems.
Which I know might sound like a dry engineering manual to some people, but reading through these sources, it's actually like a gripping detective story.
It really is. Because to understand how a modern EV can fail, and more importantly, how engineers are fighting to stop it, we have to cross 3 entirely different dimensions of physics.
Right. We're looking at high-frequency electrical stress.
Yes, and structural multibody dynamics.
And microscopic material chemistry. It's just a full journey.
It really is.
We're going to trace this phantom failure from its absolute root cause all the way to how the vehicle's computer desperately tries to mathematically catch it before you crash.
Yeah, the software side.
Yeah. And then we'll look at how the engineers physically redesign the hardware to prevent it, how the factory, locks down the assembly line.
And finally, how they just absolutely torture test these machines to the absolute breaking point.
Just to make sure that microscopic spark never reaches your highway commute. So, where do we start?
Well, the best place to start is down in the atomic weeds, really. Before anyone can fix a problem, they have to understand the physical reality of how it actually starts.
Okay.
The documents refer to the initial catalyst here as shaft voltage and bearing EDM.
Okay, let's unpack this. Because the best way I can visualize what the sources are describing is that there is literal lightning happening inside the motor's steel bearings.
Right.
But, we're talking about a sealed, grounded metal box.
Okay.
How does a lightning storm brew inside a spinning motor?
So to understand the lightning, you kind of have to picture how an electric vehicle actually gets its power.
Okay.
You've got the massive battery pack in the floor of the car, right? And that stores direct current DC power.
Which is just a flat, constant push of electricity.
Exactly. But the motor that turns the wheels, it needs alternating current AC power, which, moves in a wave.
Right.
So the component that bridges that gap is the inverter.
Okay, so the inverter is basically the bouncer between the battery and the motor.
Mm-hmm.
It takes that flat DC line and chops it up right.
Yes, it turns the power on and off incredibly fast to fake an AC wave. It uses a technique called high-frequency pulse width modulation, or PWM.
PWM, right?
But the key here is the speed and violence of that chopping. The inverter is switching thousands of volts on and off, thousands of times a second.
Wow.
Engineers actually measure this voltage change rate as dVdt. And in these high-performance systems, we are looking at a dVdt of 10 kilovolts per microsecond.
Wait, let me just pause on that number for a second because the scale is kind of hard to wrap your head around.
It's massive.
10 kilovolts is 10,000 volts.
Mm-hmm.
And it is shifting that massive amount of pressure in 1 microsecond, like
Mhm.
a millionth of a second.
Yes,
The sheer violence of that electrical shift must have massive side effects.
it absolutely does. When you shift voltage that violently, you create what is known as parasitic capacitance.
Okay, parasitic capacitance. What does that actually look like?
Well, think of the inside of the motor. You have the stationary part, right, the stator,
Hmm.
and it's loaded with copper wire carrying this violently pulsing electricity,
Right.
and sitting right inside it, separated by just a tiny air gap, is the spinning rotor.
And even though they aren't physically touching, that pulsing magnetic field is so intense that the electricity essentially like leaks across the air gap.
Exactly. The rapidly changing voltage on the stator actually induces a sympathetic voltage on the rotor. It physically couples onto the solid steel motor shaft.
Oh, wow.
So suddenly you have this stray electrical pressure, what the sources call common mode shaft voltage.
Just sitting there on the shaft.
Right. We're talking about anywhere from 70 to 370 volts of high-frequency electrical potential just sitting on the spinning shaft of the motor, desperately looking for a way out.
It wants to find the ground. And the motor casing is grounded to the chassis of the car, right?
Yes, it is.
But the only physical things touching both the spinning shaft and the grounded casing are the bearings holding the shaft in place.
Which brings us to basically the dam holding the water back. Inside those bearings, you have an inner steel ring, an outer steel ring, and little steel balls rolling between them.
But steel touching steel at those speeds would just grind itself to dust.
Exactly. So the whole thing is packed with lubricating oil or grease.
And oil is an insulator.
Right. It has a specific dielectric strength, which is really just a fancy way of saying it can resist a certain amount of electrical pressure before it gives way.
Okay, so as long as the shaft voltage stays relatively low, the oil film acts like a perfect protective wall. The electricity just can't get through.
But because of that violent inverter switching, the voltage on the shaft spikes. It pushes harder and harder against that microscopic layer of oil.
Until the oil's dielectric strength just snaps.
Exactly. The current instantly punches right through the oil film. This is the phenomenon known as EDM.
Electrical discharge machining.
You got it. The electricity literally sparks across the microscopic gap from the inner ring, through the thin layer of oil, into the steel ball, and out to the outer ring.
So it really is a microscopic lightning strike. Like, that's not just an analogy.
It's not. It is a literal high-energy plasma discharge, and it is happening inside a confined space filled with oil.
That has to get insanely hot.
Oh, the heat is so intense that it literally vaporizes the oil locally. It's essentially cooking the lubricant.
And what about the steel? The sources say it leaves microcraters.
Yeah, the plasma blasts tiny pieces of metal right off the glass-smooth steel raceway of the bearing. One spark leaves one microscopic crater.
Right.
But remember, the motor is spinning at maybe 10,000 RPM, and the inverter is switching thousands of times a second.
So you are getting localized lightning strikes thousands of times a second.
Yes. Over time, those tiny invisible craters start to overlap. You are essentially sandblasting the inside of a precision bearing. And those overlapping craters create a wave-like washboard pattern on the metal. Mechanical engineers call this fluting.
Fluting, okay.
So you have taken a perfectly engineered frictionless steel bearing and turned the inside of it into a burnt, pitted washboard.
Which means it's not going to spin smoothly anymore, right?
Not at all.
And that leads us to the second phase of this failure chain. The sources call this dynamic eccentricity and spatial harmonics.
Mm-hmm.
But physically, it's just a wobble, right?
It is a wobble, yeah. But the scale of the wobble is what makes it so fascinating here.
How small are we talking?
Well, as the bearing wears down and that washboard pattern deepens, the rotor it supports is no longer spinning perfectly true. It starts to vibrate off its center axis.
Okay.
The engineering document specifies a total indicator reading, a TIR, of greater than 0.05 millimeter.
0.05 millimeters. Wait, that is roughly the thickness of a human hair.
Exactly. You could hold that motor in your hands, watch it spin, and you would never ever see it wobbling with the naked eye.
But I'm guessing the magnetic field feels it.
Oh, it feels it instantly. The air gap between the spinning rotor and the stationary stator inside an EV motor is incredibly tight.
Right, to maximize efficiency.
Yes. And it is designed to be perfectly symmetrical so that the magnetic pull is perfectly balanced 360 degrees around the shaft.
Okay, let me try to visualize this.
Sure.
If the rotor wobbles even a hair's breadth off-center, that means the air gap is suddenly tighter on one side and wider on the other.
Precisely.
And because of the inverse square law of magnetism,
Yeah.
like moving even a tiny bit closer to a magnet makes the pull exponentially stronger.
You've got it. That uneven air gap totally messes with the electromagnetic coupling. It introduces what are called first and second order spatial harmonics.
So the magnetic field itself starts to like warp and pulse unevenly as the rotor spins.
Yes, and that is a massive problem because the car's computer relies on that magnetic field being absolutely perfect to know what the motor's doing.
Right, the computer needs to track the motor. How does it do that normally?
Well, the motor's control system is kind of like a maestro conducting an incredibly fast orchestra. It relies on a physical sensor attached to the motor shaft.
What's the sensor called?
It's called a resolver to digital converter, or RDC for short. The resolver uses magnetic flux to track the exact real-time angle of the spinning rotor, literally down to the fraction of a degree.
Because the inverter needs that data to know exactly when to fire the next pulse of electricity.
Exactly. But because of the wobble and those spatial harmonics warping the magnetic field, the resolver gets confused. The data it sends back to the maestro is, well, it's distorted.
It reads an oscillating bouncing angle.
Yeah, the motor's brain is basically getting dizzy. It thinks the rotor is suddenly jerking forward and backward.
When in reality, it's just the magnetic field distorting because of a hair-thin wobble caused by a microscopic lightning strike.
You nailed it. But the chain reaction doesn't actually stop in the motor. The wobble travels.
And this is the part of the source material that genuinely blew my mind. Like, we're moving from physics and structural dynamics straight into chemistry.
Right. They call it fretting wear and micromotion.
So the vibration from that chewed-up bearing doesn't just stay inside the heavy metal casing of the motor.
No, it's an acoustic wave. It's oscillating anywhere from 100 hertz to 1,000 hertz.
So it's like a hum.
Exactly, mechanical hum. And that hum travels out of the motor housing, along the plastic brackets, and right down the wiring harness to the low-voltage connector.
So computer plugs.
Right. The physical vibration is actually shaking the tiny metal pins inside the electrical connectors. The male and female pins are vibrating against each other.
But again, look at the scale here.
Yeah.
The document notes they are sliding against each other by just 1 to 200 microns.
A micron is 1,000th of a millimeter. We are talking about movement so small, you would need an electron microscope to verify it's even happening.
I have to admit, when I read this part, my brain just kind of short-circuited. Like, are we really saying that a 1-micron movement between two metal pins is enough to completely take down an entire vehicle's drivetrain on the highway?
It is incredibly counterintuitive, but yes, absolutely.
Just feels like the car should be more robust than that.
Well, it's not about the distance of the movement. It is about the repetition, and it is about the atomic structure of the metals involved.
Okay, break that down for me.
Sure. So most standard automotive electrical connectors use a base metal that is plated with a thin protective layer of tin.
Because tin is cheap, it conducts well,
Yep.
and it generally protects against corrosion. Right.
Right. But tin is also incredibly soft.
Right.
At the microscopic level, tin is like butter. So when those pins vibrate against each other by just a few microns, hundreds of times a second.
That microscopic rubbing is what they call fretting.
Exactly. And that fretting physically scrapes the soft tin layer right off the contact points.
Which exposes the base metal underneath, the copper.
And copper has a massive weakness. When raw copper is exposed to oxygen and the trace amounts of moisture in the ambient air, it instantly oxidizes.
It forms a layer of copper oxide.
Right. But remember, the pins are still vibrating.
So that new layer of copper oxide gets scraped off too.
Yes. Then the freshly exposed copper oxidizes again and gets scraped off again. It creates this microscopic dark debris.
And because the pins are pressed tightly together in the connector, that oxidized debris has nowhere to go. It just packs into the microscopic valleys of the metal surfaces.
And metal oxide, unlike pure metal, is a terrible conductor of electricity. It acts like a ceramic insulator.
So the electrical resistance between those two pins starts to spike.
Hugely. The sources note that a healthy connection has a resistance of under 5 milliamps. But as that debris packs in, the resistance jumps to over 100 milliamps, or even full ohms.
Which, you know, if you're talking about the main battery cable, maybe a few ohms doesn't stop the car, but these pins are carrying the resolver signal.
They are carrying millivolt sensor data. They are whisper quiet lines.
So the increased resistance acts like an acoustic dampener.
Exactly. It causes microsecond level signal dropouts. The resolver signal just vanishes into the static for a millionth of a second here, a millionth of a second there.
But to a motor spinning at 12,000 RPM, A microsecond blind spot is an eternity, isn't it?
It's massive. The system completely loses track of the rotor. The maestro just drops the baton
And there it is. Like, that is the full anatomy of the failure.
from start to finish.
Let me just recap this because it's wild. The high-speed switching induced a voltage. The voltage sparked through the oil. The spark chewed the bearing.
The chewed bearing wobbled the rotor.
The wobbling rotor vibrated the connector. The vibrating connector scraped the tin. The exposed copper oxmoles. The resistance spiked. The signal dropped, and boom, you lose power on the highway.
It is the ultimate domino effect. A perfectly logical, deeply terrifying chain of failures spanning the electrical, mechanical, and chemical domains.
So if the physical metal is scraping away, and that sensor signal drops, the motor is suddenly flying blind.
Completely blind.
And a human driver can't react to a microsecond dropout. They wouldn't even know it happened until the car just died, so the software has to catch it.
It's the only way.
How does the car's computer even know this chain reaction is happening before the whole system just grenades?
This is where we get into the software and hardware code diagnostics.
Okay.
The automotive industry categorizes safety risks very strictly, and a sudden loss of motor torque on the highway falls under ACEL D.
ACEL D. What does that stand for?
Automotive Safety Integrity Level D. It is the absolute highest classification of hazard.
Meaning?
It means if this system fails ungracefully, the risk of fatal injury is extremely high.
Wow. So the system can't just, like, throw a check engine light and hope for the best.
Absolutely not. It needs the most rigorous diagnostic coverage imaginable. And the first line of defense is genuinely poetic, I think.
Oh, yeah.
The system uses mathematics to literally listen to the hum of the motor. The sources refer to this as FFT and THD monitoring.
Okay, I want to break this down carefully because the math here is fascinating.
Sure.
The system uses high-speed analog to digital converters, ADCs, right, to constantly sample the electrical current coming back from that resolver sensor.
Yes, it's taking thousands of snapshots of that electrical wave every single second.
And in the background, the processor is running an algorithm called a fast Fourier transform, or FFT.
Right. Now, for listeners who haven't sat through an advanced calculus or signal processing class recently, an FFT is one of the most important algorithms of the modern digital age.
Truly.
It takes a complex, messy signal, a waveform that has a bunch of different frequencies all matched together, and mathematically separates it into its individual components.
I always like to think of an FFT like a magical smoothie machine in reverse.
Reverse smoothie machine. I like that.
Yeah, like if you put a strawberry, a banana, and an apple into a blender, you get a messy combined pink smoothie. An FFT takes that pink smoothie and mathematically pulls it back apart into a perfectly whole strawberry, a whole banana, and a whole apple.
That's a great analogy.
Or, to use an audio analogy, it's like listening to a massive symphony orchestra playing all at once and using a math equation to isolate just the sound of the second violinist sitting in the back row.
That is exactly how it works. Now, apply that to our motor. Remember that 0.05 millimeter wobble caused by the chewed-up bearing.
Right, the physical eccentricity.
Because that physical wobble constantly changes the magnetic resistance in the air gap, it actually modulates the electrical current. It adds a very specific low-frequency hum to the electrical symphony.
The wobble creates a new instrument in the orchestra.
Yes. And by running that FFT, the software can isolate that specific new hum. It calculates what is called the total harmonic distortion, or THD.
Okay, so if the THD starts to slowly rise over time,
The software can mathematically hear the physical mechanical wear of the bearing.
that is incredible. It knows the bearing is failing before the driver feels a thing.
And long before the electrical signal is actually lost, it can throw a predictive maintenance flag.
So it tells the dealership, hey, this bearing has microscopic craters in it. You need to swap it out at the next service, entirely avoiding the highway failure.
Precisely. Using mathematical signal processing to diagnose a physical structural defect.
But let's say it's too late. Like, let's say the vibration gets worse rapidly, the fretting wear on the connector accelerates, and the signal starts getting heavily corrupted.
Okay.
How does the car know what data is real and what is just a glitch? Because the sources detail a protocol called a multi-source plausibility check.
Right. This is where the ACEL D safety architecture refuses to trust any single point of failure. It triangulates the truth by constantly comparing three completely independent speed readings.
So it's kind of like interrogating three different witnesses to a crime, right? You put them in separate rooms and see if their stories match.
That's a really good way to look at it. Witness number one is the resolver, the RDC.
Which is our physical sensor sitting on the motor shaft, reading the magnetic angle.
Yes. Witness number 2 is entirely virtual. It is a software algorithm called a sensorless slide mode observer, or SMO.
Wait, how does software calculate the speed without a physical sensor?
It uses the laws of electromagnetism. When you spin a magnet inside a coil of wire, it generates electricity. This is basically how a generator works.
Right.
But an EV motor is already using electricity to spin. However, as it spins, it simultaneously generates a reverse voltage called back electromotive force, or back EMF.
Oh, interesting.
So the SMO software looks at that back EMF voltage and mathematically calculates exactly how fast the motor must be spinning to generate that specific voltage.
Okay, so witness 1 is physical magnetism. Witness 2 is software math based on back EMF. And who is witness 3?
Witness 3 is totally external to the motor. It is the actual wheel speed sensors, the exact same ones the anti-lock braking system uses, feeding data into the motor controller via the car's high-speed NFD network.
So the computer just sits there asking all 3 witnesses, how fast are we going?
Right. If all 3 say, we're doing 10,000 RPM, everything is fine.
But if that fretting wear kicks in and the connector starts dropping the signal, the physical resolver suddenly starts screaming that the motor speed is jumping wildly.
Yeah, from 10,000 RPM to 0 up to 12,000 RPM and back to 0 in a matter of milliseconds.
The computer instantly cross-references the other 2 witnesses.
And the software-based SMO and the physical wheel speed sensors are both sitting there perfectly calm saying, no, the back EMF is stable, the wheels are turning smoothly, we're doing exactly 10,000 RPM.
The computer spots the lie.
Instantly. It identifies that the physical resolver sensor has been compromised by mechanical vibration or oxidation, and it immediately isolates that data.
It stops listening to witness 1 and just drives the car using the virtual SMO data.
Exactly. But there is a limit to how long you can drive on virtual data. If the signal is completely destroyed, if that copper oxide packs the connector so badly that the sensor drops offline entirely, the system has to initiate a shutdown.
Right. The sources call this catching the fall.
And this has to happen fast. The document mentions a fault-tolerant time interval, an FTTI, of less than or equal to 60 milliseconds.
To put 60 milliseconds in perspective for you listening, it takes a human being about 300 milliseconds to blink their eyes.
So in 1/5 of the time it takes you to blink, the car's computer has to detect a microscopic wobble, isolate a failing sensor, realize the signal is dead, and safely shut down the propulsion system.
Because if it takes like 65 milliseconds, the consequences are catastrophic, right?
Absolutely. If you have a motor spinning at 12,000 RPM, loaded with high voltage electricity, you cannot just hit the off switch.
Why not? Like if the sensor fails, why not just pop the digital breaker and kill the power?
Because of that massive magnetic field we talked about earlier, an electric motor is basically a giant inductor. It stores energy in its magnetic field.
Okay.
If you instantly sever the connection to the battery while the motor is spinning under load, that massive magnetic field collapses instantly.
And when a magnetic field collapses that fast,
It dumps all its stored energy back into the wires as a massive, uncontrollable voltage spike.
oh wow, it would act like a lightning strike in reverse. It would just blow the inverter to pieces and potentially fry the main battery pack.
It would literally turn the car into a high-voltage bomb. So the software has to catch the fall gracefully. It executes what is called a stepwise active short circuit, or ASC.
But the exact execution depends on the physics of the vehicle at that exact millisecond, right? Like the sources say it checks the speed first.
Yes.
If you were going slowly, say under 20 kilometers per hour, what does it do?
Well, at low speeds, the motor isn't spinning fast enough to store a lethal amount of energy. The back EMF is low, so the system simply opens all the circuits safely. It's called freewheeling.
So the magnetic field dissipates harmlessly, the motor just spins down, and the car rolls to a stop.
Exactly. But if you are on the highway, if you are doing 80 kilometers per hour or more.
That is where the stepwise ASC kicks in. Stepwise meaning it happens in phases.
Right. Phase 1 lasts just 1.5 milliseconds. The inverter deliberately short-circuits 2 of the 3 motor power phases together.
Wait, it shorts itself out on purpose.
Yes. By shorting 2 phases, it creates a temporary buffer that prevents a massive current surge from rushing back to the battery.
Okay, and then what?
Once that stabilizes, literally a millisecond later, it enters phase 2. It drops into a full 3-phase short circuit.
What does a 3-phase short circuit actually do physically to the motor?
It essentially traps the energy inside the motor. The spinning rotor is still generating electricity, but because the wires are shorted together, the electricity just loops back into the stator coils.
So the magnetic field pushes against itself.
Yes, it turns the spinning motor into a massive internal electromagnetic brake.
It uses the motor's own inductance to safely clamp that wild overvoltage. The document says it limits the voltage to safely under 720 volts.
It absorbs the kinetic energy safely, slowing the car down without blowing the battery or the inverter. And it calculates and executes this multi-phase, high-voltage dance in 60 thousandths of a second.
It is a staggering marvel of software engineering.
Yeah,
It is basically a digital airbag for the powertrain.
it really is.
But, as brilliant as that software is, if you take a step back, it is fundamentally a Band-Aid.
Sure.
The diagnostic software catches the failure, and it saves your life, but it doesn't prevent the car from breaking down in the first place. You are still stuck on the shoulder of the highway.
Which is exactly why the software is only one piece of the puzzle. If you really want to solve the problem, you have to go back to the drawing board.
You have to physically redesign the hardware so that the lightning strikes and the oxidation never happen at all.
Right. This brings us to the actual mechanical and electrical engineering blueprints.
The DFMEA, right? The Design Failure Mode and Effects Analysis.
Yes. How do we build a motor that is immune to its own physics?
So the first mandate is obvious. You have to deal with that high-frequency shaft voltage. You have to ground the lightning before it hits the bearing oil.
Exactly. The design specification here, DG-PCS ME003, mandates the use of a dedicated shaft grounding ring, an SGR.
Okay, how does an SGR work?
Well, the core problem with the EDM bearing current is that the electricity has nowhere else to go. The path of least resistance is straight through the lubricating oil to the grounded casing.
Right.
So the engineers simply provide a better path. An SGR is essentially a highly conductive ring fitted with a carbon brush that physically rides against the spinning motor shaft.
Because carbon is highly conductive.
Yes, and it can handle the friction of a shaft spinning at 12,000 RPM without wearing away too quickly. It uses a small spring to maintain constant physical contact.
So now, when that high-frequency common mode voltage builds up on the shaft, it hits the carbon brush.
And the brush is wired directly to the chassis ground. It gives the voltage an easy, entirely harmless path to dissipate.
It completely bypasses the bearing.
Exactly. You cut off the discharge loop at the source. If the voltage goes through the carbon brush, there is zero pressure on the oil film.
No sparks inside the bearing, no micro craters on the raceway, no washboard fluting.
The root cause of the wobble is eradicated.
And the sources also mention a secondary option if they don't want to use a carbon brush, right? Hybrid ceramic bearings.
Right, which is more of a material science solution. If you don't want to drain the electricity, you just make the barrier impenetrable.
Instead of steel balls rolling inside the bearing, they use balls made of silicon nitride, a type of advanced ceramic.
And ceramic is a perfect electrical insulator. It doesn't matter how high the voltage spikes. It physically cannot spark through a ceramic ball. Problem solved.
Both the carbon brush and the ceramic bearings stop the wobble at its source. But engineers are inherently paranoid, aren't they?
Highly paranoid.
Right. The DFMEA process assumes that somehow some vibration will still occur. So they can't just fix the bearing. They also have to fix those low-voltage computer connectors.
They have to prevent the fretting wear and the oxidation.
The sources referred to this next step as building a better bridge. They completely ban standard pure tin terminals for these critical sensor lines. Because, as we said, tin is too soft, it scrapes away too easily.
So what material would you suggest they use instead?
Well, if tin is too soft and oxidizes, my first instinct would be to just use solid copper pins. Copper conducts perfectly. It's what the wires are made of anyway.
It conducts perfectly, sure. But consider the physical reality of a solid, pure copper pin vibrating thousands of times a second.
Okay.
Pure copper is highly malleable. It bends. It suffers from metal fatigue very quickly. Under that kind of high-frequency stress, a pure copper pin would just fatigue and snap off entirely.
Right. It needs to act like a spring. It needs to hold tension, so they alloy it.
Right. The spec says they upgrade the base metal of the terminal to beryllium copper.
Beryllium copper. That sounds expensive.
It's a legendary alloy in aerospace and military applications. By adding a small amount of beryllium to the copper matrix, you fundamentally change its crystal lattice structure.
So it gets stronger.
It gains an incredibly high yield strength and severe fatigue resistance. It acts like a very stiff, nearly indestructible spring that won't snap under vibration.
But beryllium copper is still mostly copper. It will still oxidize if it's exposed to the air, right?
Yes, which is why they still have to plate it. But they force an electroplating of greater than or equal to 1.7 microns of soft gold over a nickel barrier layer.
The nickel acts as a hard shield, but the gold is the magic ingredient, isn't it?
Gold is a noble metal. At the chemical level, it simply does not react with oxygen. It does not rust, it does not tarnish, it does not oxidize in air, period.
And the spec specifically calls for soft gold. Why soft?
Because soft gold provides exceptional self-lubrication. Even if the connector vibrates aggressively, the gold just smears and slides smoothly against the other layer of gold on the opposing pin.
Well, that makes sense. There's no hard scraping, no debris generated, no oxygen reaction, and therefore no microscopic resistance spike.
It's a brilliant material solution.
But they don't just stop at upgrading the metal. They completely redesign the physical geometry of the connection itself.
Right. The spec mandates a move away from standard flat blade pins to a hyperboloid or crown spring structure.
Okay, so the standard electrical pin you find in most cars is a simple flat metal blade that slides into a tight metal slot, right? It relies on a single point of friction to maintain contact.
Exactly. But a hyperboloid net. This is where the engineering gets almost artistic. A hyperboloid is a mathematically double-curved surface.
Think of a Chinese finger trap.
Yes. Instead of a flat slot, the female socket is made of a woven basket of tiny angled wire springs. When the solid male pin pushes into that basket, those angled wires stretch, twist, and wrap entirely around the pin in 360 degrees.
The geometric result is that instead of one single point of contact, you now have 10 to 20 independent parallel contact points running along the length of the pin.
It really makes me think of crossing a river. The old tin blade connector is like trying to balance on a single rusty tin plank over a rushing river. If a strong wind or a vibration causes that plank to wiggle or crack, you are falling in the water. The signal is completely lost.
But this new hyperboloid structure, it is a 20-lane, solid, gold-paved suspension bridge.
Exactly. If a microscopic vibration causes one specific wire to momentarily lift off the pin, you still have 19 other independent gold pathways perfectly carrying the signal.
It creates an immense amount of physical redundancy at a microscopic scale. You have basically engineered the vulnerability entirely out of the system.
And you combine that with strictly enforcing microtolerances, restricting the static and dynamic runout of the structural casings to under 0.05 millimeters to guarantee the air gap symmetry. And the theoretical design is bulletproof.
Yes, the theoretical design.
Right.
Because on a computer screen, in the CAD software, you have drawn a masterpiece. You have carbon brushes draining the lightning, you have 20-lane gold-plated suspension bridges for data, and you have tolerances engineered to a fraction of a hair's breadth.
But the CAD model isn't the car.
Exactly. Here is the massive reality check. None of that beautiful theory matters if the guy on the factory floor gets frustrated and hits the bearing with a mallet to make it fit onto the shaft.
Which brings us to the transition from design to manufacturing. The PFMEA, the process failure mode, and effects analysis.
You have to lock down the factory floor.
The controls put in place during manufacturing have to be just as obsessive, if not more so, than the ones in the design phase.
Because humans make mistakes. The first rule of the factory floor for these EV motors is essentially ban the hammer.
Yeah, the sources talk extensively about mandating concentric servo pressing.
When you are dealing with a design that relies on 0.05 millimeter tolerances, manual assembly is just a massive liability.
Even traditional automated brute force pneumatic presses are banned. A pneumatic press just uses air pressure to slam a part home until it hits a physical stop.
And if that bearing is sitting even slightly crooked when the pneumatic press slams down,
you induce microscopic stress fractures in the steel. You warp the inner ring. You basically induce physical fatigue before the motor has even been plugged in.
So they replace the brute force with automated concentric servo presses. These are electric, hyper-precise pressing machines.
Yes. And what I find absolutely fascinating is that these machines don't just push blindly. They are equipped with sensors that actively monitor a force displacement curve in real time.
Think about what that means for quality control. The machine's computer is plotting a real-time graph.
Right. On the x-axis is the distance the bearing has moved down the shaft, measured in micrometers. On the y-axis is the exact amount of force required to push it.
So it knows exactly how hard it should be pushing at every microscopic fraction of a millimeter. It expects a perfectly smooth, predictable curve of resistance.
Right. And if the machine senses even a tiny anomaly, a microspike in pressure because the bearing is snagging, or a slight axial skew that drops the resistance,
It instantly locks down. It stops the press in milliseconds, pulls back, and flags the part as defective.
it removes the human element of, just push a little harder to make it fit. It completely prevents microscopic assembly damage from ever entering the vehicle.
But getting the parts together perfectly is only half the battle, right?
Mhm.
Once the rotor is assembled, they have to ensure the perfect spin.
The source document strictly outlines a 100% dynamic balancing test on a two-plane system.
You cannot just assume a heavy chunk of steel, copper, and neodymium magnets is perfectly balanced just because the math says it should be.
No, the factory runs 100% of the rotor assemblies, every single one that comes off the line, through a dynamic balancing rig.
How does that work?
They spin the rotor up to operating speed and use ultra-sensitive lasers and accelerometers to measure the vibration across two distinct planes at the ends of the rotor. They are mapping the exact distribution of mass.
And the standard they hold it to is staggering. The document mandates that residual imbalance must be restricted to an ultra-strict G2.5 class.
G2.5, yeah.
I had to look this up because it sounded intense. G2.5 is the exact same ISO balancing standard used for high-speed gas turbines and steam turbines. They are balancing car parts like they are commercial jet engines.
They absolutely have to. Consider the physics of a motor spinning at 16,000 RPM. Centripetal force increases with the square of the velocity.
Right.
At those speeds, even 1 single gram of uneven weight distribution on the edge of the rotor will generate enormous, violent outward forces.
You'd act like an unbalanced washing machine on the spin cycle, just tearing its own bearings apart.
Exactly. By restricting the imbalance to G2.5, the automated machines can precisely laser drill tiny amounts of metal away or add microscopic counterweights until the rotor spins like glass.
It prevents the motor from literally shaking itself apart from the inside out.
Exactly.
Okay, so the motor is perfectly pressed and perfectly balanced. But my absolute favorite factory floor detail, and the one that honestly sounds the most unhinged when you first read it, is what the sources describe for sealing the connectors.
Ah, the glowing grease protocol.
Right. The automated optical inspection of the chemical seal. So they have these beautiful beryllium, copper, gold-plated hyperboloid connectors. They're already practically immune to oxidation.
But that's not enough for the engineers.
No. They use automated micro-greasing machines to inject a highly specific automotive-grade conductive fluorosilicone grease.
The document actually names it. Niogel 760G mixed with a copper inhibitor, precisely injected directly into the pin sockets.
The fluorosilicone is highly resistant to extreme temperature swings, and the grease forms a perfect, airtight chemical seal around those 20 gold contact points. It entirely blocks out any trace of atmospheric oxygen, road salt, or condensation.
But they don't just inject the grease and trust the machine. They literally mix a UV fluorescent tracer glowing paint into the grease itself.
And then, on the assembly line, they pass every single connector under an automated optical inspection, an AOI camera that blasts it with ultraviolet lasers.
The computer vision algorithms check the glowing footprint of the grease to guarantee 100% internal coverage, with absolutely zero microscopic leaks or spills on the outside of the plastic housing.
You seemed skeptical of this step when we first talked about it.
I do. It sounds like complete sci-fi overkill. Mixing glowing UV tracer fluid into connector grease just so a computer vision camera can verify a dollop of lube on a pin.
It feels like something out of a NASA clean room assembling a Mars rover, not a car factory in the Midwest building commuter vehicles.
I understand why it feels like overkill, but let's connect this back to the absolute beginning of our conversation. You have to remember the stakes of the domino effect.
The ASLD rating.
Exactly. Walk through the chain again. What happens if the greasing machine stutters and leaves a microscopic gap in the grease coverage?
A single micron of the gold plating could potentially get scratched during assembly, exposing a tiny speck of copper to the air inside that gap.
And that tiny speck of exposed copper oxidizes. That localized oxidation acts as an insulator, which causes a 100 milliamp resistance spike across the pins.
That resistance spike drops the resolver signal for exactly 1 microsecond.
And that microsecond drop tricks the computer into thinking the motor is failing, which triggers an ASLD high-voltage stepwise active short circuit.
which violently shuts down the propulsion system while the driver is merging onto the highway at 80 miles an hour.
Yes. When a microscopic scratch on a metal pin can take down a 4,000-pound vehicle at highway speeds, visual confirmation of chemical seals using UV lasers isn't NASA overkill. It is an absolute non-negotiable safety requirement.
Wow. Okay, I concede. When you frame it backwards from the highway crash to the UV laser, the paranoia is entirely justified.
Every single step of that process is a hard-fought lesson in reliability. Engineering is written in blood and breakdowns. They don't implement glowing grease unless someone, somewhere, figured out that missing grease caused a catastrophic failure.
So the engineers have designed a mathematical and metallurgical masterpiece. The factory has built it flawlessly under the watchful eye of lasers, UV cameras, and servo-press force curves.
But how do they actually prove it works?
Right. A CAD model and a clean room are one thing, but a car lives outside in the mud, the ice, and the potholes. How do they know this delicate, gold-plated system will survive the real world?
They torture it. They subject it to environments far worse than any human driver ever could.
Welcome to the final phase, the crucible, DVP&R, which stands for Design, Verification, Plan, and Report. This is production validation.
And reading through these tests, it honestly reads like an interrogation manual for heavy machinery.
The validation phase is critical because it has to simulate the entire 15-year life cycle of the vehicle, hundreds of thousands of miles of real-world abuse in a matter of weeks.
And the brilliance of the DVP&R outlined in these sources is that it perfectly mirrors the root causes we explored in the very beginning.
They physically force the lightning and the wobble into the system to prove that the brains in the blueprint actually hold up.
Let's start with how they test those connectors. The shake and bake, which follows the notoriously brutal LV214 automotive standard.
They take these gold-plated UV-greased connectors and bolt them to a specialized testing rig. They subject them to severe randomized vibration,
sweeping the frequency from 10 Hz all the way to 2,000 Hz while pulling 35 meters per second squared of gravitational acceleration.
That is violent, bone-rattling vibration. But they don't just shake it at room temperature. The rig sits inside an environmental chamber.
While it's shaking, they violently swing the ambient temperature from negative 40 degrees Celsius deep, Arctic, freezing straight up to positive 150 degrees Celsius, which is hotter than boiling water.
Freezing them, boiling them, and violently shaking them, all at the exact same time. The thermal expansion and contraction alone would tear most plastics and sheet metals apart.
And they don't do this for an hour to see if it holds. They monitor this continuous torture for over 500 uninterrupted hours.
3 solid weeks of shaking and baking, and the passing criteria are absolutely ruthless.
You can't just have a connector that still looks intact at the end. After 500 hours, they measure the electrical contact resistance. It cannot have increased by more than 1.2 milliohms from its original baseline.
1.2 million. The tolerance for degradation is virtually zero.
Furthermore, during the entire 500-hour test, the system monitoring the data flow must register absolutely 0 micro-interruptions in the signal that lasts longer than 1 single microsecond.
If the signal drops for 2 millionths of a second on day 14, the design fails.
But the final physical test of the LV214 standard is my absolute favorite because it shows how deep they go. After the electrical tests are done and it passes, they take the physical connector, embed it in hard resin, and physically slice it open down the middle with a diamond-tipped precision saw.
They polish the cross-section and place it under a scanning electron microscope.
They are looking at the molecular layers. The test only passes if the microscopic layer of soft gold is completely intact, with 0 evidence of wear through to the nickel barrier or the beryllium copper base metal.
It is utterly ruthless. But they don't just torture the connectors, they torture the entire motor itself. The sources detail the lightning test, officially called high DVDT endurance testing.
Remember the high-frequency switching stress from the inverter, the 10 kilovolts per microsecond that caused the spark?
Right.
They take a fully assembled motor and hook it up to a specialized, oversized testing inverter specifically designed to aggressively and relentlessly blast the motor with that exact 10 kV per microsecond electrical stress.
They intentionally feed it the lightning.
Yeah.
They're trying their hardest to blow past the carbon shaft grounding ring and spark the bearing.
Exactly. And they do it while running the motor fully loaded on a dynamometer, forcing the internal copper windings to bake at over 130 degrees Celsius, simulating a car towing a heavy trailer up a steep mountain pass.
And they hold it there for more than 1,000 uninterrupted hours.
6 weeks of continuous high-voltage lightning strikes at towing loads. And when the 1,000 hours are finally up, they rip the motor apart.
They pull the bearings off the shaft, and they don't just eyeball them. They put the steel raceways into a scanning electron microscope equipped with energy-dispersive X-ray spectroscopy.
They are hunting for the chemical and physical signature of EDM, electrical discharge machining. To pass this validation test and clear the motor for mass production, there must be 100% zero fluting.
Zero microscopic washboard patterns. Zero microscopic EDM plasma craters on the steel raceway.
And even if the visual inspection passes, they reassemble the motor and test the acoustics. The total harmonic distortion, the THD of the resolver signal, cannot have increased by more than 1% from its baseline.
Think about what that 1% threshold means. If the THD increases by more than 1%, it proves the physical geometry of the bearing has degraded.
It means the carbon brush failed to drain the lightning, the EDM cratered the bearing, the physical wobble was introduced, and those spatial harmonics are warping the magnetic field.
A strict 1% acoustic limit mathematically guarantees that the physical root cause has been eradicated.
Which brings us to the final and perhaps most mind-bending test of the entire DVPNR process, the matrix simulation. The sources refer to it as acyl fault injection, running on a high-fidelity FPGA hardware-in-the-loop rig.
This is where they validate the software brains, the ASIL-D safety protocols, the multi-source plausibility checks, the stepwise active short circuits.
You cannot safely test that software on a real physical test track. If you intentionally induce a microsecond resolver failure while a test driver is doing 80 miles an hour and the software has a bug, the motor explodes and the driver is killed.
So they take the car's physical control computer, the actual metal box that goes into the car, and they plug it into a supercomputer.
Specifically an FPGA, a field programmable gate array. It is hardware that can be programmed to act like an entire virtual electric vehicle. It perfectly mathematically simulates the physics, the inertia, the magnetic fields, and the electrical resistance of the motor in real time.
They spin this digital simulated motor up to a screaming 12,000 RPM in the matrix. And then the test engineers get to play God.
They type a command and maliciously inject a 100 million resistance spike into the digital sensor signal. They literally tell the car's computer that the physical rotor just magically skipped 180 degrees instantly.
They're simulating the absolute worst-case physical scenario, a total catastrophic loss of the resolver data due to severe fretting wear while the motor is under maximum load at top speed.
And the software in the physical box has to react to the virtual lie. The passing criteria mandate that the system's safety management unit must instantly diagnose the failure, cross-reference the virtual witnesses, isolate the lie, and execute the stepwise active short circuit.
It has to digitally lock down the system, clamping the simulated voltage safely below 720 volts and limiting the massive short-circuit current to less than 550 amps.
And tying it all back, it has to complete that entire diagnostic and physical clamping process within the FTTI window. 60 milliseconds.
1/5 of a human blink. If it takes 61 milliseconds, the virtual motor blows up, the test fails, and the software engineers go back to the drawing board.
The symmetry of this entire engineering process is genuinely incredible. The crucible of the testing phase perfectly mirrors the terrifying physics of the root cause we started with.
They force the lightning in the test lab to prove the carbon brush design actually works.
They force the massive temperature swings and vibration to prove the gold plating and the UV grease hold the chemical line.
And they force the catastrophic signal dropout in a digital matrix to prove the software can catch the fall when all else fails.
It is a closed-loop system of complete engineering paranoia.
So let's step back and summarize this massive journey we've just been on. We started this deep dive with a microscopic spark of electricity and a tiny physical wobble smaller than a grain of sand.
We watched as that spark chewed through hardened steel bearings, created an acoustic vibration that traveled down cables, and literally scraped microscopic layers of tin off electrical pins,
threatening to completely shut down a modern electric vehicle on the highway.
But we also saw how human engineering fights back. We explored a war fought entirely on the microscopic level against sparks, friction, and heat.
We saw brilliant mathematical software running Fourier transforms to listen to the harmonic distortion of a magnetic field to catch a failure early.
We saw physical hardware redundancies, carbon brushes to drain electricity to the chassis, beryllium copper springs, and gold-plated hyperboloid nets to protect millivolt data.
And we saw the draconian zero-tolerance controls of the modern factory floor. From force-monitored servo presses that refuse to push a crooked bearing to glowing UV chemical seals inspected by lasers.
All of it validated in a terrifying crucible of extreme heat, vibration, and digital matrix simulations. It fundamentally shifts how you view a car.
It makes you realize just how much hidden obsessive complexity sits right under the floorboards of a modern EV. Every smooth, silent highway cruise you take is the direct result of millions of hours of high-frequency physics mitigation.
It is a testament to the old engineering adage that true reliability is invisible. You only notice the engineering when it's absent. When it works perfectly, it just feels like magic.
Which leaves me with one final, very provocative thought to mull over. It was inspired by a very brief, highly technical note right at the very end of our source document.
Oh, right. The Python model.
The text casually mentions using Python programming tools to build a 3D, high-frequency common mode shaft voltage transient coupling model.
They're building a digital twin of the magnetic and electrical fields.
Exactly. They are basically creating a perfect digital replica to calculate the precise safety boundaries of that internal lightning strike without ever needing to build the physical motor first.
If our math is getting so good
Yeah.
and our computing power is making these digital twins so perfect,
Well, the physical torture testing we just talked about, the 1,000-hour oven bakes, the shaking rigs, the diamond saws, will all of that eventually become obsolete?
it is the ultimate frontier of engineering.
Will the cars of tomorrow be fully designed, built, degraded, and stress-tested to destruction, entirely inside a digital matrix, before a single physical piece of metal is ever mined from the earth or manufactured in a factory?
Given how fast these algorithms and quantum simulations are evolving, the answer to that might be a lot closer than we think.
Ponder that the next time you hear a brand new EV silently glide past you on the street, it really makes you appreciate the invisible, microscopic war being fought every single time you press the accelerator.
Absolutely. The complexity is breathtaking.
Well, that is all the time we have for this deep dive. As always, keep questioning the world around you, especially the intricate parts you can't see. We'll catch you on the next one.